Okay, so what I have here in front of me is the worksheet that I handed out yesterday for you to try and complete on your own. And so what I'd like to do is zoom in on different sections of it and sort of talk our way through it. So I'll be going through the video and pausing at different times so that I can readjust what we're looking at and have a closer discussion on some specific components of it. So make sure that you have this in front of you and pause the video if you need to grab it. Okay, so as I mentioned in class, this diagram actually begins with pyruvate oxidation, right? And so let's just do a quick recap of that. So as we know, pyruvate is going to enter the mitochondrion from the cytoplasm, and then we're going to take a carbon atom and remove it. That process has a special name. It's called decarboxylation. I think it makes sense. Decarboxylate, so D meaning take away from, and then you're going to take the carboxyl group off. And when you do that, you're also going to be taking some hydrogen from food, and you're going to be attaching it to NAD+. And that's going to give us this NADH that we're seeing over here. Then we see our pyruvate connect with or become acetyl group. The 2-carbon acetyl group combines with our coenzyme A, and we call that now acetyl coenzyme A. So that's actually what this thing is called right here, and it's going to enter into the Krebs cycle. So I'm going to write that down. So right here, this is our pyruvate. And there's only one of the two shown here. We need to know that this is happening twice. I'm actually going to color it in using my blue marker here so that we can keep track of where its particles are ending up. Although this won't be exactly right, it'll help you to see what's coming and what's going. All right, so this thing that we have now, this 2-carbon compound, is our acetyl coenzyme A. Now, if we look down here at this on the left, this 4-carbon compound here, I'm going to highlight it in red. This is a really important molecule in the whole cycle because it's the one that gets regenerated. So it's actually, well, it's oxaloacetate. And oxaloacetate is this 4-carbon compound that is going to attach to acetyl coenzyme A in the first step of the cycle. So this, in red here, oxaloacetate is going to join with our 2-carbon acetyl group to form another molecule, the first molecule in the Krebs cycle. So if this is these are my 4 carbons coming from oxaloacetate, then I have the 2 from acetyl coenzyme A. Coenzyme A leaves, and the acetyl group that remains attaches, forms now, I have this 6-carbon compound, and it's called citrate. Now, immediately after that, what we see is a number of things happening to citrate. Let's take a look at this first paragraph up on the right and take stock of where we are so far. So the Krebs cycle begins with that acetyl coenzyme A combining with oxaloacetate, as we just spoke about. So here's oxaloacetate combining with acetyl coenzyme A. The coenzyme A leaves first, and the remaining acetyl group will combine to make the 6-carbon compound citrate. Okay, so what we're going to see next is a series of modifications to citrate. And as this happens, we're going to be releasing some CO2. We're going to be decarboxylating citrate. And in the process, that's going to release some energy, and we're going to be able to produce some ATP as a result. Okay, so citrate is going to eventually be broken down, rearranged, all of that, so that we end up back with oxaloacetate at the end. So what I want to do next is I want to go through those remaining reactions. So I'm going to pause the video, readjust my screen, and we'll take a look at what happens with citrate. So in the next phase, what we're going to see is citrate reorganizing itself. It will look the same on this diagram, but if you refer to the diagram in your Nelson textbook, then what you'll see is that it actually is an isomer of citrate now. It's still 6 carbons, but it's no longer citrate, it's called isocitrate. So it's an slight difference in rearrangement. And what that does is it just enables the molecule to be able to rid itself of a carboxyl group in the form of CO2. So that's exactly what we see. We see a decarboxylation happen. So there's one of our CO2s that originated from the acetyl group coming off. And so it actually ends up being one of the carbons on oxaloacetate, and rearrangements happen. So it's not actually straight off of this acetyl group if you look really closely. That's a little bit beyond where we need to be, but important nonetheless. So the energy in the decarboxylation of isocitrate is used along with one of its hydrogens and its electrons to reduce NAD+ to NADH. So there we've created another electron carrier that we're going to make use of in the final stages of cellular respiration. So in the next step, we have 3 carbons from oxaloacetate and our 2 from the acetyl group remaining. This molecule now is referred to as alpha-ketoglutarate. So that's a little mouthful, but let's write that down. So the symbol, the Greek letter alpha, and alpha-ketoglutarate. We spell that right, glutarate. Okay, and that alpha-ketoglutarate is a 5-carbon molecule, so it may be useful for you to write down right beside it. Not that counting is really hard, I guess, but you need to know how many carbons are in each of these. It's important. So again, we're going to see alpha-ketoglutarate, the 5-carbon compound, be decarboxylated. And again, that process is going to result in some energy released, and that will be used to add some electrons to reduce NAD+ to NADH. Okay, and then what we're left with, well, now we're down to a 4-carbon compound again. However, it is not oxaloacetate. It is a different molecule now. So, so we end up with 4-carbon compound. Again, I'm coloring it just for ease. Eventually it rearranges and the color will all be red because it's now oxaloacetate again, and so we start over. This molecule, this 4-carbon compound, is called succinyl coenzyme A. So what you'll see right over here is that the enzyme coenzyme A comes in. It's going to attach to this 4-carbon compound that remains after alpha-ketoglutarate is oxidized, and what we get is succinyl coenzyme A, and it's a 4-carbon compound. So the neat thing now that I think is worth noting is that acetyl group, really, we've created 2 carbon dioxides. So really the CO2s that, the 2 CO2s that made up the acetyl group, though they didn't originate from that acetyl group, are still basically, in terms of accounting, been released from the molecule. Right? So if this would happen again, for the other acetyl group, we will have broken down glucose essentially completely. So from there, though, succinyl coenzyme A is not oxaloacetate. We need to be able to get another molecule of oxaloacetate happening, and so all the rest of the steps are really meant to just get us back to that oxaloacetate so that we can begin the cycle again. But the good news is that in that process we're also able to make some other useful molecules, and so it's definitely worth mentioning. So we see that coenzyme A now is able to leave. Okay, so our coenzyme A leaves, and when it leaves, that releases a little bit of energy, and that energy is used to take a molecule of GDP and create a molecule of GTP. Now, you may be saying, well, what the heck is a GDP and GTP? Well, you should hopefully gather that they must be some kind of diphosphate and triphosphate, and you're right. Okay? The A stood for adenosine triphosphate, indicating the nitrogenous base that's involved. GDP is guanosine diphosphate and guanosine triphosphate. So this is a different nitrogenous base that's produced just because it's easier to produce directly from the process. But what you need to know is that eventually it is converted into ATP as well. So, you know, when I look at this whole cycle, I can see that overall the entire Krebs cycle only produces 1 ATP per acetyl group. And so for the 2 acetyl groups resulting from pyruvate oxidation, I'm going to make 2 ATP. Okay, so now once that happens, that process happens, I end up with a molecule of succinate. So succinate, and at this point I'm just going to start to color them all in the same color because it doesn't really matter. I think you get the gist of what's going on in the first few stages. So I end up with succinate. Okay, which is also a 4-carbon compound. I'm not going to go any lower than that because oxaloacetate over here at the beginning is a 4-carbon compound. Through the rearranging of succinate, I'm going to be able to pull off some hydrogens from it and create another 4-carbon molecule. Again, this is all in the hopes of being able to get to oxaloacetate. So succinate ends up being oxidized. The hydrogens are used to reduce FAD to FADH2, as we can see here. By pulling off those hydrogens, I create a molecule of fumarate. Okay, which is another 4-carbon compound. And there, from fumarate on, I'm going to create another form. It rearranges to form what we call malate. And finally, to get back to oxaloacetate, there's a rearrangement of malate. Malate is going to rearrange. It's going to be oxidized NAD plus. Notice they're missing the plus sign here. NAD plus is going to be reduced to NADH due to the liberated hydrogens from oxidizing malate. And now I'm back to oxaloacetate, and the whole process is ready to start over again. What I would advise you to do is to go through and start by memorizing the order of the names. And then once you memorize the order that the names come in, the rest of it I think will fall together for you. Let's fill in the last little section of this worksheet. Okay, so we see that overall per cycle there end up being some CO2s that result. 2 CO2s via decarboxylation are released as waste. We end up with a total of 2 NADH per turn of the cycle and 1 FADH2, and they're going to go on in our electron transport chain and make some mega ATP. There is some energy, however, that's able to be released in this process. Eventually it becomes ATP. We see that here. And so the glucose molecule is going to produce 2 molecules of ATP in the Krebs cycle. Not overall, but we're talking here just in the Krebs cycle. Okay, only 2 of them. And that's because one turn makes 1 ATP, but we start with 2 pyruvate, which become 2 acetyl coenzyme A's, starting the cycle. Okay, so we'll talk more about the accounting of things. I hope that this made sense to you and that you'll be ready for your quiz on Friday.